All right. This is the first of two videos that we'll have in Chapter 22 of Openstax Astronomy. And in this video, we're going to focus on what happens to stars from when they first reach the main sequence to what's really determining when they leave the main sequence. And we're going to focus on the fact that we can figure out how long that phase is going to last, how long the main sequence lifetime will be, based on the mass of those stars. And then we can use star clusters in order to actually test our ideas. So we're going to learn what star clusters are, why they're so helpful to us, and then we'll figure out how they help us check stellar evolution as a theory. And then in the next video, we'll learn a little bit more about what happens after stars leave the main sequence. Now, we're going to start out by trying to think about a couple of things. First of all, we saw this image already in Chapter 21 video, where we mentioned the fact that stars get to the main sequence after a certain amount of time based on their mass. High mass stars, there's a lot of gravity, and so they're being crunched down very quickly in order to get onto the main sequence, whereas low mass stars, it takes them a really long time to get to the main sequence. Main sequence stars will just sit there and burn hydrogen into helium through fusion until they run out of hydrogen in their core. So that should sound a little bit ominous. It's foreshadowing. But before we get to what happens when they run out, I want us to think about a really key idea here that we're going to see if we have the intuition for, and it's fine if we don't, and then we'll move on and we'll make sure that we do get the right ideas into our head. So a pause and think question for us. If a more massive star is burning hydrogen to helium, similar to the sun, but more mass, do we expect it to have a longer or shorter lifetime than our sun? So what I want you to do is I want you to pause the video right now and put down your initial thought, and then I'll add a couple of thoughts, the sort of discussion aspect into this, and then you can decide if you agree with your initial instinct or not. So pause first and just really quickly decide longer or shorter. Maybe even convince yourself to write it down in your notes. Okay. So, some things to keep in mind and consider. A more massive star has to fight more gravity, so it has to go through its fuel faster. So that's one thing to consider. But a separate kind of competing idea is that a more massive star means that it actually has more fuel available. So which one of those does our sort of intuition tell us wins out? So do more massive stars live longer because they have more fuel? Or do they live shorter because they're going through their fuel so much faster? So I want you to think about those two possibilities. All right. Now, it's not a perfect analogy, but it's a pretty good analogy, is to compare the fuel efficiency of a giant pickup truck with a little small fuel-efficient sedan. The giant pickup truck definitely has a bigger fuel tank, but if we start them with full tanks of fuel on a highway and we just let them go, which one's going to have to exit the highway first? Hopefully your intuition for that's a little bit stronger than with stars necessarily. The giant pickup truck has such a massive engine, it's going through its fuel so much faster. And so it will run out of fuel first and have to go exit and go to a gas station. We can use that same kind of intuition for stars. Even though more massive stars have a bigger fuel tank, a bigger core of stuff to go through fusion, they go through their fuel so much faster that more massive stars die sooner at a much faster rate than just kind of linearly. Now is going to be the right time for us to try the lecture tutorial Star Formation in Lifetimes, or if this is an on-campus flipped classroom course, we'll be doing this lecture tutorial the next time that we're in class. But a pause and think question for us, either before you start the lecture tutorial or after. because this particular question is just having us kind of remember what it is we talked about in chapter 21. Main sequence stars begin life as which of these options? So pause the video and think through. All right. Hopefully we said number 2, a cloud of gas and dust. We call those clouds of gas and dust nebulae, or we're talking about the interstellar medium and dense cores and giant molecular clouds, all of those important terms from chapter 21. It was a short video with some important vocabulary to keep in mind. But the answer here, main sequence stars begin life as a cloud of gas and dust. After you've tried the lecture tutorial, this question will be answerable in a more easily thought about way. But we're given the lifetimes, the main sequence lifetimes of 3 different stars. Star A is going to live for 45 billion years. Also could be written as 45,000 million years to make it more easily able to be compared. Star B is going to be a main sequence star for 70 million years. And star C will be a main sequence star for 2 million years. Now, with just this information, we should now, after the lecture tutorial, have a really good understanding of the compared masses of these stars. Not necessarily a number value for their mass, but an understanding of which star has more mass. So pause the video and think about it. Okay, so since high mass stars die sooner and low mass stars live a longer lifetime, star C has the greatest mass out of these 3 options. And if we look at these numbers and kind of compare them to what we've talked about for the sun, which is 10 billion years, we can actually tell just from these numbers that star A has less mass than the sun because it lives longer, and stars B and C both have more mass than the sun because they live shorter. Now, what's really important for us to understand is that the mass of a star determines what happens to that star completely. Mass will tell us if we even make a star at all, because there is a upper limit to stars that's about 120 solar masses. That upper limit is not as well researched because there are so few stars that are created at those large scales to begin with. But the point is, if a dense core has more mass than that, what's far more likely is that it will actually just make a binary system. There's a lot of stars in binary systems, actually more than stars by themselves. And so if that dense core has too much mass, it'll just kind of split and make 2 stars. Mass will also tell us if we're at the lower limit for stars. We actually talked about this lower limit when we talked about the spectral types back in chapter 17-18. If we go to masses that are too low and objects that are too low temperature, we're no longer talking about a star. Instead, we're talking about a failed star. Do you remember what that one was called? You can pause if you want to look it up. It was a brown dwarf, that sort of fuzzy line between stars, which were higher mass than brown dwarfs, and planets, which were lower mass than brown dwarfs. So, mass tells us if we can make a star, but the mass of a star also tells us how large or small it's going to be based on how much gravity is pulling on it, and how quickly a star goes through its fuel. We talked about the mass-luminosity relation. The mass of a star directly determines how quickly it has to generate energy in order to balance that force of gravity. Now, this link here is a really fun little website that I want you to play around with kind of after the set of videos this week and almost after the set of videos next week. But I wanted to put it here because one of the really key things about this cool website is that the only thing that you have to input for it to be able to tell you everything that happens to a star plotted on an HR diagram is the mass of that star. That really kind of hits home the idea that a star's mass tells us what will happen to it. Now, if a whole lot of stars formed at the same time as each other, then what we should expect to see from this information that we've generated is that the highest mass stars will die first, and the lowest mass stars will take a longer period of time, and they'll stay on the main sequence for longer. This image is very similar to the one that we saw for protostars, but this is now how many years it takes for a star to leave the main sequence. We can look at star clusters to figure out if our understanding of star formation is on the right track, with more massive stars should die first and lower mass stars should live longer. And the reason that star clusters are so useful is because we have a whole bunch of stars that all formed at the same time. Now, before we get into how we're using them to test our understanding, we need to make sure that we understand that there's two types of star clusters. We're going to learn about them now and kind of make a note to ourselves that we're going to have to revisit these ideas in chapter 25, but they're here in chapter 22, and so we're going to go through them now. One of the two types of star clusters is called a globular cluster or a globular cluster. These things are huge. They contain hundreds of thousands, sometimes a million stars, all clumped together in one small part of space or one large part of space. All of the globular clusters that we find here in the Milky Way are all older. They are all filled with stars that are like 11 billion years old or greater. There's very little gas or dust in these globular clusters. It's mostly just stars. And because there are so many of them, that gravity is kind of pulling them to be shaped like a big spherical blob of stars. That's the kind of globe or glob shape. In chapter 25, we'll discuss a lot more the implications of where they're found in the Milky Way. We haven't learned the word halo for the galaxy, but we'll kind of have this as something you can look back to for chapter 25. These globular clusters are found outside of the galaxy disk in the halo of the Milky Way. And because they are so massive and have so many stars that are shining, they're very easy to find in the sky. And the Milky Way galaxy, our own galaxy, has about 150 of them total. The other type of cluster is called an open cluster. So the one shown here is nicknamed the jewel box. And we can see that there's a countable number of stars in these open clusters. There's dozens, maybe 100 stars. The Pleiades star cluster that we talked about as our example reflection nebula, that's an open cluster. There's just a couple dozen stars there. For open clusters, they tend to be younger in size. Stars form in clusters, but there's not a lot of gravity, so they can be easily dispersed. When we see an open cluster, we're typically seeing all of those stars having newly formed and often still in the cocoon of gas and dust that they formed from. These tend to be found in the disk and spiral arms of the galaxy because that's where gas and dust is still easily available to form new stars. And something that is going to be more useful for us to think about later on, but more heavy elements are found in open clusters than globular clusters. Stars in globular clusters tend to be mostly hydrogen and helium with very little other elements. Our sun, on the other hand, probably formed in an open cluster 5 billion years ago that has since dispersed, and it has a higher percentage of these elements. 2% is fairly significant compared to the tiny amounts in globular clusters. Okay. Now, the reason that these two types of clusters, and again, the distinction is going to be more important to us in chapter 25, but we have to introduce it now. The reason that star clusters, no matter the type, are useful to us is because we now have a nice set of stars that all formed at the same time, which means they have the same age. That's really important. And they're all the same distance away from us, which means we can look at a picture of these stars, and ones that look brighter are physically more luminous, and ones that look dimmer are physically less luminous. That is not a statement we can make of most stars in our sky. When we look at the stars in our night sky, the ones that look bright tend to be the ones that are close to us. But because they're all the same physical distance away in space, they're all roughly the same distance from Earth, the differences in apparent magnitude can be directly translated into luminosity. Very important for us and very useful. Okay, so this cluster here only has cooler, low-temperature stars. Normally, our HR diagram goes up to like 20,000 degrees on the horizontal temperature axis. And what we're seeing is only stars that are those reddish or yellowish stars. The luminosities here are also much lower than the HR diagram that we're used to having. And we know that our typical HR diagram, if we think back to when we introduced it, or we think back to the deeper look video, it's got like a kind of S-shaped curve from upper left down to lower right, and that's not what we're seeing here. We're seeing a really weird shape instead. So I want you to pause the video and try to think through a little bit about what we're seeing here. Why does the HR diagram have this weird shape? And what happened to all of the more massive stars? All right. The second answer should be one that, if we think back to what we've been talking about so far, is fairly straightforward. The more massive stars have died. We'll talk about all of the cool things that happen to them when they die, but they're gone. Low mass stars live for a really long time, so all of these stars are still kicking, but all of those high mass stars, they've gone through their whole life cycle and they're finished. This weird shape comes from the fact that when stars leave the main sequence, they leave the main sequence and become colder and larger stars. And we'll talk more about that in the next video when we focus on what the sun is going to do when it runs out of fuel. But what we see is stars, when they leave the main sequence, they become colder and larger. They move up to the upper right. And they do so in a way that the ones that are already way, way up in the upper right, they're about to kind of finish their lives and be gone out of this picture. And the ones that are just leaving the main sequence, if we kind of line up those stars' expected lifetime, we can figure out the age of all of the stars. Now, let's take a step back. This is a important and kind of tricky thought here. Age and lifetime are not the same thing. In a star cluster, all of these stars have the same age. It's like going to high school. Everybody in your same grade, in 9th grade, is all roughly the same age. But that doesn't mean that you're all going to live exactly the same length of time. In a cluster, all stars have exactly the same age, but they have a variety of lifetimes. That's based on those stars' masses. The low mass stars are going to live a super, super long time, hundreds of billions of years, longer than the age of the universe. And the highest mass stars, they're going to live a couple million years and they'll be gone. They'll have lived a great, very short, live fast, die young kind of life. Now, the main sequence turnoff point is where the stars here are starting to leave the main sequence. And the reason why we really like this star cluster here is if we look at where my cursor is, it's lined up with 6,000 Kelvin, that's the temperature of the sun, and 1 solar luminosity, that's the luminosity of the sun. This particular star cluster, if a star exactly like the sun were in this cluster, it would be at that main sequence turnoff point, which means that a star that should live 10 billion years on the main sequence is about to leave the main sequence. That means the whole star cluster is 10 billion years old. This set of more stylized pictures might help us recognize that a little bit better. And again, we're basically peeling off the main sequence from high mass stars down to low mass stars. And the third example here is showing a main sequence turnoff point right at about the location of where the sun would be. Because if the sun were here, it would be about to die, and so it would have gone through its whole 10 billion year lifetime. This is really helpful for figuring out how to determine the age of stars. If we can get a sense of how stars of a certain age look by directly making that measurement with star clusters, then we can get the estimate of stars by themselves in space. It's kind of similar to the mass-luminosity relation, but without so clear an equation that could be written for it. In the next video, we'll be talking more about what happens, why we leave the main sequence in that direction, and what happens once the Sun and other low-mass stars do leave the main sequence. All right, I'll see you then.